Well, greetings. I'm Michael. This is my dog Moo. I, I was advised to use this photo because it will make me seem just a little bit more friendly. So, thank you, Matt, for the introduction. At Cerebras, we're a startup company. We're about 200 engineers right now, and we've built the world's largest and most powerful computer processor. And it's also the first supercomputer that has been designed from beginning to end for artificial intelligence and deep learning. So tonight I'm going to talk a little bit about how we got involved on this endeavor and some of the things we learned along the way and what we're seeing in the field. This is the largest wave that has ever been surfed. And this is also the state of our industry right now. What we see is artificial intelligence is transforming every aspect of technology. And the surfer is everyone in this room. As data scientists, you're powering AI, and there's been no better time to be involved in the field that you are. So at the outset of our company, before we went on to an endeavor to do this, we thought maybe a computer engine could help deliver some of the promises that this field seems to be able to deliver. And we, at the beginning, before you're a stealth company, you go and seek advice from everyone you know, and they end up telling you all of the reasons why what you're thinking about is completely crazy and maybe you shouldn't be involved in it. So I'm going to go through that first. So it's clear to, hopefully to everyone, that there's a deep relationship between computation and intelligence. And neurons are doing something that seems to be computable. But no one knows how it is that billions of neurons aggregate together and actually result in an intelligent system. And meanwhile, there's just a ton of research coming out right now. This is a field that's advancing very rapidly. When you're doing computer hardware, it takes years from the time that you have a design concept until you can see that product out in the market. And so one of the first things we heard was maybe we ought to just wait for the researchers to decide what it is they actually want to do before you start building a machine. And that seemed like the wrong advice. When the field is rapidly changing, that's when they will welcome innovations. And so what we decided was to bring together the best minds we could in computer hardware and software and algorithms and engage in a process of co-design to try to bring it all together and do something that can actually move the field. The second interesting fact is our brains use only 20 watts of power to produce their artificial intelligence. And that suggests that maybe the entire problem is only one of software, that we have just tons of computing power and maybe there's not a need for any new equipment. Then once the right algorithms are known, it will work on our 386s. Well, that was also sort of Turing's conjecture when he invented the computer. He created the Turing machine. He put with it the challenge of the Turing test. Is there a program that will make this device intelligent? And on one hand, he proved that any algorithm that you can invent whatsoever can be run on this machine. It's a machine that works by executing a computer program. It has a sequence of instructions, and it reads and writes to memory, which is represented by these spools of tape right here. But one observation is that although this can do anything, it has no claim about being an efficient way to emulate something like a human brain. And in fact, when we look throughout the history of computing, it has never happened that a new important workload has come along, and the correct answer to that workload was to use some pre-existing equipment that had been designed to do something else. And yet that's exactly the state that many of us find ourselves in today, where graphics processors are being used to solve our large optimization problems. So to look a little bit more about this, here's just a thought experiment on computing a bird's brain. This is a Eurasian rook, and he has about 1 billion neurons. Each of them fire on average one time every second and connect with 10,000 other neurons through their synapses. So if you want to take a classical von Neumann architecture and just evaluate the inference side of this, forget about training the bird, you would have a processor, and you would have all of the state of your neurons off in some memory. And just the act of loading that state into the compute engine, doing some calculation, and then pushing the updated state back takes about 25 nanojoules per access. So it's pretty easy to multiply this out, and you see that, that this bird, which doesn't have a huge metabolism, would require over 0.5 megawatt just for the memory access power to do this computation. And that's enough to power several city blocks. So maybe there's a sign that we're not on the right track with the architecture we have in von Neumann computers. So when we looked at this, we thought, how can we develop something? What are the ingredients of a computer processor that would be right for this kind of application? And since it's still a field that's evolving, we have to look and see what are the fundamental things that you're making use of. And so two things stand out. One is the scale at which you're operating is tremendous. So we're in a field where we're doing things such as connecting pixels from a video stream into a large statistical engine and getting out the commands that drive a car. And so this is just an enormous computation. And the second observation is that the models we're producing don't work based on instructions. It's not a central operator that says, do this, do that. Instead, it's the data that flows over our model and a simple feedback equation that tells that data how to manipulate and transform the model that seems to be the heart. And so we decided to build a machine that was as large as we could, that had memory interleaved directly with the computational substrate, no fetching memory from far away, keep it right near the data. Let it be configured to execute some of these feedback equations, and the bandwidth would be tremendously important because our field is all about data in motion. So this is the part we built. This is my co-founder, Sean, at Hot Chips. This is the world's largest processor. It's a full computer wafer. It is 462 square centimeters, and that's a new unit of measure. So before this, processors had always been measured in square millimeters. It's the first part that has over 1 trillion transistors, and we're at 1.2, and it has 400,000 sparse linear algebra cores on it. Each one of them is a completely independent programmable entity. It integrates some memory. There's 18 gigabytes of memory right on that silicon wafer, and it gives an unprecedented 9 gigabytes per second, sorry, 9 petabytes per second of memory bandwidth. I'm still thinking in the old units. The cores connect to each other with 100 petabits per second of interconnection bandwidth. So these are a lot of big numbers, but just how big is this? Here's our wafer drawn to scale next to the largest graphics processor on the market. And when we showed this, the world got pretty excited. So there was a large press splash. And in part, that's because this had been presumed to be impossible to achieve. There's always defects when you manufacture a wafer this large. And the computer processor industry in general chooses to make these monolithic machines where every part has to be perfect. And so they end up throwing out a whole bunch of silicon. And for us, it was actually the data science and the models that provided the answer to this. By having 400,000 independent cores is perfectly fine if we have a few hundred defects on there. And it's only our job to route the information flows around those defects. So this is an example of sort of the definition of the problem, providing the answer that allowed the industry to move forward. So having a processor suited to the job was a necessary but not sufficient task for us. No one before had ever put a processor that large on a motherboard, and so we had to also make a system to house this thing. This is the CS1. It's what you would put in a data center. Let's open it up. So you can see the engine block at the back. It's that colorful piece. There's only one wafer mounted in there, and the entire rest of this is about cooling and power delivery. Here's the engine block up close. This maybe looks a little bit different than what you're used to seeing when you open up your computer. And that's because traditionally you put the power supply next to your processor and you run power across the motherboard. we would have 40,000 amps, and that would actually melt the part if we chose to do it that way. So we had to bring some of the geometric thinking beyond how we think geometry in the models into this 3D structure. And so these black and green parts in the front are our power transformers, and they're delivering power perpendicularly to the compute substrate. And there's a cold plate on the back that extracts the heat energy. And so you see a flux of entropy perpendicular to the compute. And it's only information that flows across the surface of our computer. So one thing we learned in this is that there were a whole bunch of hard problems we had anticipated, and by and large, they were all solvable. The processor redundancy, like I said, the answer came from the data models we were using. Reticle stitching to get above the optical limit of how you manufacture these things, that worked the first time we tried it. Designing sparse algebra cores is an exercise in logic and algebra. And even implementing novel networks was a fun task, but you can see in the background image here how some of the layers of a neural network are applied. But when you go to bring something into existence, you have to confront not just those problems you anticipated, but everything that also happens along the way. And so it maybe is ironic that this nanolithography that you use to produce these processors is one of the pinnacles of human technology. It is super fragile, and you can crack these things without trying too hard. So just the act of applying power to this was the crux of our problem. And there are kind of hundreds of dimensions of variables that would control this, from how you dope the metal to how thick the material is, what kind of the pitch of your holes and wires. And ordering any of this, it takes about 2 months from the time that you have an idea to make a design change to get it back in your lab. So we spent over a year trying to solve this problem. And in the end, what we learned is you have to look for and be accepting of data everywhere. Just sweeping the parameter space of how you manufacture wasn't sufficient to solve it. But we engaged with some experts, and if you get optical on your crack, this is the side of the wafer showing where one of these fractures originated. And then if you look at the point of origin, you can see with the electron microscopy, we learned something that was interesting. As you use a laser to vaporize the silicon to create the holes, which we use to bond this wafer to the cold plate, that material ends up, the vapor condensing back down. And no one knew this. Right on the surface of the silicon, it created a texture that makes it hard to withstand some of the shear forces. And so the lesson here is, once you find the mechanism that's causing a problem, it's usually pretty easy to find an intervention you can use to manufacture. And I think this I've seen in data science areas as well. So having solved this, we were left with a machine that was pretty impressive on most of the metrics, being larger, more cores, 10,000 times the memory bandwidth, and 33,000 times the fabric bandwidth. But how do you program something like that? So again, the simpler, I think simpler than programming a conventional computer where you have to specify millions of instructions. Here we're just taking these structural graph models that come out of some Python framework. There's a two-step procedure. We match it to our kernels, which are these parametric shapeable entities. Maybe do a convolution you can apply across 100 cores or 100,000. And then there's an optimization problem to map these kernels to make full use of the compute substrate. I'll show it in action. This is a graph that maybe some of you recognize as having convolutions. There's 3 convolutions down the main arc and 1 on a residual path. If I zoom out, I'm sure everyone will recognize this. Lo and behold, this is the ResNet 50 benchmark. And so we match that against kernels. These 17 blocks right here are the 17 residual segments of the network. And we have an optimization solver that places these over the 400,000 cores. You can see the layers occupying different physical regions of the processor. And we can show the gradient information flow. These are solved with gradient descent coming back over from the loss layer out to the surface. So it's pretty unusual in Silicon Valley to have your first customer be the US national labs. But I think that corresponds to some of the excitement in the industry, and has been really amazing for us to see our product, even as new as it is, being applied to improve cancer treatment with the world's largest cancer database, learn new properties of black hole physics from gravitational waves, and Lawrence Livermore has integrated into their Lassen supercomputer. However, this is all what we think of as just a good start. We aspire to make whole new categories of learning algorithms possible. And as computer infrastructure providers, we don't know the complete right formulation of what your learning algorithm needs to be, but we don't think that your thoughts should be constrained by the limitations of a graphics processor. And so we're hoping to present out an easier way to get new experiments out at scale. And I wanted to close with this ancient map. So I think this also represents the state of our field today. Here be dragons is what you put when there's some unexplored territory and you can only imagine what you might find. So we know there are some cool phenomena out there, and we're right now just at the first leg of this journey. And I want to invite everyone here to think, what would you like to build when there are machines out there where the paradigm matches the way you want to work? And one day, not too far from now, when we have exaflop scale computing, what problems would you like to apply this to? Thank you.
Thank you very much. Fascinating. Just one question from me, as we're a little over time, and I'll open up to people.
Okay.
Without bad mathing your competitors, there are a variety of companies, including startups, that have emerged around in this space, like GraphCore and Savanova and all the things. Can you maybe help us contrast the approaches, and are those doing different things for different people, or are you guys all going after the same opportunity? And in that case, how different are you?
Yeah, I certainly won't. There's plenty of space in the field, in the computer hardware field, for there to be multiple innovative plays. What we're doing is aimed towards the largest problems at data center scale, and fundamentally new research. If you have more data that you can train with right now, that would be where our machine comes in. And I think there are specialists who work only in low power inference, who want to have edge devices, who are trying to put intelligent processors in cars, and who are taking different cracks at the same thing, who maybe want the most compatible with the existing software ecosystem rather than fundamentally new innovations. So I think that there's plenty of room at this point while the field is advancing, and that's part of what makes it exciting, is the developments in data science and AI have made it possible for us to do this innovation.
Great. All right. Do we have one question over there?
Which material are you using? Which material are you using for the wafers?
What material?
Are you using? Yep.
It's a silicon process. It is fabricated at Taiwan Semiconductor, which is one of the world's large major fab houses. What was innovative about it isn't necessarily how the circuit itself was made, but that we're able to cross the reticle boundaries. So typically you make these wafers, and it's a game of Humpty Dumpty. You make a big compute surface of all the same chip, and half of them don't work. You slice them and throw away the defective ones. And so because we were able to solve yield, we can present all this compute without ever cutting the parts up and then trying to put them back together.
Yeah, thank you. How does this will compare with quantum computing? I know that we're in different time frames there, but curious to know if quantum computing is coming to production, how would this compare to that?
I think quantum computing is super interesting. It's one of these fundamental areas of research. So if you think neuromorphic or quantum or optical computing, all of that stuff is promising. The things that also there's space in the hardware world for. We think that because that's primary research, that's a good 10 to 15 years out, whereas what we looked to do was to take technology we could manufacture, maybe difficult, but all achievable, so we weren't trying to invent any new law of physics to power our machine.
I had one last one here.
Yeah.
Yep.
So one of your early diagrams had a neural network. So I'm not sure if your architecture allows for modifiable synapses. Are you trying to model that as well?
So each of these 400,000 cores that are on there are completely independent programmable entities. And that was something we had to do because we, building this early on, didn't know everything that was going to be in the field. So we chose to not do any optimization for a special case like a 3x3 convolution, etc. Instead, we chose to look at the fundamentals. How is data moving across the cores? What kind of feedback equations and rules might you want to put into it? So yes, you could model things like that.
All right, great on this
Okay.
note. Thank you so much.
Thank you.
This was terrific.